So in this example, it says, let C be a unit circle centered at the origin, traced out counterclockwise, and then evaluate this vector line integral for these two vector fields. Great. We're using the same C for both of these, so let's just parameterize C once and for all, so then we can use it for these two calculations. So C is a unit circle centered at the origin, and we've parameterized this a few times now. We can write R of t as cosine of t and sine of t. It's traced out counterclockwise and only once, so that tells us that t goes between 0 and 2 pi. Great, so extracting the x of t and the y of t from there, we get x is cosine and y is sine. And then I'm going to need the derivatives, so x prime is minus sine and y prime is cosine. All right, and then now let's go off and calculate the vector line integral of this first vector field. So I'm going to have minus y comma x times dr. Dr is dx dy. Okay, so I'm just kind of writing everything out here so we can review how this actually works out, but we actually don't need to do all these steps. If I scroll back up, this is really what we're going to end up calculating anyway, but I'm writing out all the steps to review them. So over here I get minus y dx plus x dy, and we can see that this is where I need the information from the derivatives that I calculated. So dx is, well, let me substitute in what y is first. So y is sine of t, so this is minus sine of t. And then dx is x prime times dt. X prime times dt. And then x over here is cosine t. Cosine of t. And then dy is y prime of t times dt. Cosine t dt. Everything is now in terms of t. T ranges from 0 to 2 pi, so those are my limits, 0 to 2 pi. And then now I simplify. Here I get sine squared. Here I get cosine squared. I'm adding them, and I know sine squared plus cosine squared is 1. So I get integral from 0 to 2 pi of 1 dt. And that just becomes 2 pi. Okay, so for number 1, I'm going to say answer, because I'll have to erase this to give myself room. Answer is 2 pi. So in other words, if we were thinking about this vector field, and we plotted this vector field, and then we drew this unit circle, and we looked at the work done by the field in moving, this fictitious particle around this curve once, the answer would be 2 pi. I could give you units, but they're not going to mean much because I don't have other units in the problem. But I've plotted the vector field here that we're dealing with. This is the same one we saw in the previous lesson. And so you can see if I drew any curve here, let's keep it in blue, any circular curve here around the origin. This is the unit circle of radius 1. And I imagined a bead on this circle, then the vector field vectors really do push around this bead, and they do some work in doing so, right? There's some energy expended to do that. And we've calculated that energy to be 2 pi, again, ignoring the units. So that's just a very, very quick and rough idea of what is going on and what we're measuring. Okay, so let's try this again for the second vector field here. So I'm just going to erase, I'm going to keep the parameterization the same. That's what is implied in the problem. And I will go back and erase things as they need erasing so that I can keep some of this writing here. So the vector field is 2x, 2y. So that goes over here, 2x and 2y. And then, so I'm integrating slightly different things now. So I have a 2x and a 2y. First thing I'll do is I'll pull out the 2, because that's common to both. And then here, basically, what's different is what these first terms are. Dx is still x prime times dt, so that's this term. Dy is still y prime times dt, so that's this term. Those don't change. What changes is 2x and 2y. So now I have x, which is cosine of t, and then I have y, which is also cosine of t. So that's over here. Oh, sorry, that was y prime. So y is sine of t, which is over here. And then now we recalculate. So notice that this is negative cosine times sine, and this is plus cosine times sine. So I get 0. And therefore, my integral is 0. So the answer for number 2, answer is 0. Okay, so what could that mean? Well, so I have plotted here the vector field. This is the field 2x, 2y. This one on the left, remember, was the field negative y and x. So when I drew the unit circle here, we did see, just based on the picture, that if we pretended there was a bead here, you know, these vector field arrows really were pushing the bead around and doing some work in the physics sense, generating motion across some distance. If I draw a circle here, the unit circle, you can see what's happening, which is that all of the vectors are everywhere perpendicular to this unit circle. So if I place a bead on the circle, like right here, and then I ask, is it going to move? The answer is no, because no portion of the vectors here are ever tangent to this circle. So there's no force, if you will, being applied tangent to the circle to move the bead along the circle. Instead, all the force being applied is orthogonal to the circle. So, you know, the bead can only quote unquote move that way or this way. You know, the vector field is moving radially outward, so the bead is not going to move because I'm restricting it to move only along this unit circle. We will later on consider what happens. You know, we're throwing away effectively all of the motion perpendicular to our curve. We're only looking at, again, as we said earlier, motion tangent to the curve. But, you know, there is something to be said about the fact that this vector field is pushing only outward and does not yield motion along the curve. But again, we'll get to that later on. For now, this explains why this integral is 0. This vector field, despite, you know, there's a bunch of vectors everywhere, for the particular curve we've drawn, does not generate any motion along this curve. No work is done. Okay, so that's this example. So now I want to go back to, you know, broaden our horizons here and start thinking about why did we get a 0 here, no work, and why did we get a non-zero here, you know, a positive number specifically.